Good morning. And okay, let's start with this problem. Now we want to maximize the utility, which is Q1 to the power of alpha and Q2 to the power of beta, subject to the budget constraint P1 Q1 plus P2 Q2 equals Y. So the first step to solve this problem is to put down the utility function here, Q1 to the power of alpha, Q2 to the power of beta, plus a Lagrange multiplier, and the resource, which is Y here, minus P1 Q1 minus P2 Q2. Alright? And the first order conditions, Lagrange lambda. So partial Lagrange, partial lambda, we have lambda here. And the result would be Y minus P1 Q1 minus P2 Q2. We set it to 0. And the second order condition, the second first order condition is to differentiate Lagrange with respect to Q1. So we have alpha, Q1 alpha minus 1, Q2 to the power of beta still, and we have Q1 here. So we have a negative lambda P1, also 0. And Lagrange 2. We have beta Q1 to the power of alpha, Q2 to the power of beta minus 1, minus lambda P2. The same reason here. Alright, so we have all the first order conditions, and then we want to solve what? We want to solve Q1 star, Q2 star, and lambda star. So we just take the last two, Lagrange 1, Lagrange 2, and which would be alpha Q1 to the power of minus 1, Q2 power to the power of beta. And this term actually is U1, right? The marginal utility of Q1, divided by beta Q1 to the power of alpha, Q2 power of beta minus 1, which is the marginal utility of Q2 equals lambda P1, lambda P2. Is that right? And we may rearrange this to be alpha over beta, and we have a Q2 and Q1 here, right? After some manipulation. Is that clear? And lambda will be cancelled out. So we have P1, P2. There is a trick to solve this problem. Alpha over beta, and we rearrange again P1, Q1, P2, Q2. So, is everyone happy with this? From here to here? So, what does this term mean? What do you think this term represents? What is P1, Q1? The money you spend on good one, or the expenditure on good one, right? The total money you spent on good one. You buy this many Q1, and for each you have to pay P1. So it's the total expenditure on Q1, on good one. Is that cool? Okay? So this is the expenditure on good one and the expenditure on good two. And you know the total expenditure the sum of these two terms would be y. Is that clear? So the expenditure, the ratio of the expenditure, the relative expenditure would be alpha to beta. Okay? So P1 Q1 is actually alpha plus beta alpha y. Is that right? Let me give you some numerical example. Suppose that the expenditure, the proportion for the expenditure on good 1 to the expenditure on good 2, say 2 to 3. So totally you spend 2/5. It would be 2/5 y. You spent this much money on the consumption of good 1. Get it? Once again, the ratio of P1 Q1 to P2 Q2 equals alpha to beta. Alright? So the proportion on expenditure will be alpha to beta, which means because the P1 Q1 plus P2 Q2 equals y due to the budget constraint. So we may have this result. Alright? You got a pie, this is your y. And alpha to beta. So this is on good 1. And this is on good 2. If it is alpha to beta, then totally it would be alpha plus beta, right? So alpha over alpha plus beta is the proportion you spend on good 1, right? Then we will have Q1 star equals alpha over alpha plus beta y over P1. And by the same logic, P2 Q2 equals alpha plus beta y. And Q2 star would be beta over alpha plus beta y. Oh, sorry. Y over P2. Okay? So you see Q1 is a function of P1, P2, and y. And you see Q1 is a function of P1, there's no P2, but we have y here. And also, Q2 is a function of P1, P2, and y, function of exogenous variables. So now we have y here, we have P2 here, but we don't have P1, which means Q1 star is a function of P1, P2, and y. And Q2 star is a function of P1, P2, and y. I just copied that from this slide. Alright? So now let's check the direction of the impact. So the more Y you have, the more Q1 you will decide to consume. I mean the optimal solution, the optimal level of Q1 you wanna consume. Okay, so this would be a positive impact. Is that clear? And also positive for Q2. So the more income you have, the more Q1 you consume. So Q1 is what kind of good? Is normal or inferior? Good. Normal good, right? So Q1, we know it would be a normal good. And also Q2 is a normal good. Is that right? And for P1, which is in the denominator now, so the higher the price of good 1, the less the quantity of good 1 you would decide to consume, right? The higher the price, the less the quantity. So it is a negative impact. The influence would be negative, right? So satisfying what? The law of demand. Is that clear? Demand of Q1 and P1. So is the price-quantity relationship would be negative. The higher the price, the less the quantity. So also for this. So both goods satisfy what? The law of demand. Is that right? And it will be 0, which means the impact of the price of good 2, P2. P2 has no influence at all on Q1. And P1 doesn't influence Q2. Right? Because you don't see any P2 in the function, in the solution. Also, you don't see any P1 in the solution, which means these two kind of goods, we call this a utility function of Cope-Douglas. So for Cope-Douglas utility function, commodity 1 and commodity 2 are neither substitutes nor complement, right? Because the price of another good doesn't affect the good, the quantity, or the quantity demanded for this good. So they are neither substitutes nor complements. Okay? So from the solution we have, we may give some judgments, or we may conclude something. The first conclusion would be, oh, they are normal goods, and the second would be, oh, they both satisfy the law of demand. And the third, good 1 and good 2 are neither substitutes nor complements. Alright? And what about if we want to know, or we want to have the solution of lambda star? How can we do that? Lambda star. We may use the second or the third first order condition. If we use the second one, lambda star would be alpha q1 to the power of alpha minus 1 q2 to the power of beta over p1. This would be lambda star. And star. Alright? So it will be alpha, and q1 star will be alpha over alpha plus beta y over p1 to the power of alpha minus 1. And q2 star would be beta over alpha plus beta y over p2 to the power of beta. And we have a p1 in the denominator. So let me see. Yeah. So we'll have y over alpha plus beta to the power of alpha plus beta minus 1. And alpha to the power of alpha, beta to the power of beta. Right? Because we have alpha to the power of 1 and alpha to the power of alpha minus 1. So it would be power of alpha. And we also have p1 to the power of alpha and p2 to the power of beta. We may put them in the denominator, right? So this would be lambda. Any question here? And lambda measures the effect of a change in y on the optimal value of the objective function, which means lambda here would be the marginal utility of y. And you will see this term. Do you think this term is a positive term or negative term? It's a positive term, right? It's positive. Okay? So the marginal utility of y would be a positive term. So it's a little bit complicated, but not very hard to find, to derive. All right? So the trick here, you need to notice that the trick here is the expenditure on good 1 would be a proportion of y. It's a proportion of y, right? And the the expenditure on good too is another proportion of y. And these two proportions sum to 1. Right? Any question here? What about this? If we have 3 types of goods, 1, 2, and 3. Can we just apply the same procedure, the same logic to this problem? Let's see. Lagrange would be Q1 alpha, Q2 to the power of beta, Q3 to the power of gamma, minus a plus lambda, and the resource y, minus P1, Q1, minus P2, Q2, minus P3, Q3, right? And Lagrange lambda, y minus P1, Q1, minus P2, Q2, minus P3, Q3 equals 0. Lagrange 1, which will be alpha, Q1 alpha minus 1, Q2 beta, Q3 gamma minus lambda P1. Lagrange 2 would be beta, Q1 to the power of alpha, Q2 to the power of beta minus 1, Q3 power gamma minus lambda P2. What about the fourth first order condition, which would be gamma, Q1 to the power of alpha, Q2 to the power of beta, and Q3 to the power of gamma minus 1 minus lambda P3. Right? So check the similarity. Okay? And then let me use this one. From this two, we will have alpha to the power, anyway, one and 2 and 3 and 4. So by 2 and 3, we may have this conclusion, right? We may have this result. Is that okay? All right? And what about 3 and 4? We will have beta and Q3, gamma Q2, which will be P2 over P3. This will be from the third and fourth first order condition. And, of course, from the second and the fourth would be alpha to the power of gamma and Q3 over Q1, which will be P1, P3. This would be 2 to 4. All right. So we may have easily the conclusion that P1, Q1, P2, Q2, P3, Q3. Right? Is that clear? The proportion you spend on commodity 1, commodity 2, commodity 3. I mean the relative expenditures will be alpha to beta to gamma. Okay? So, what about Q1 star? It should be very easy, right? It would be alpha over alpha plus beta plus gamma y over P1. And Q2 star would be beta over alpha plus beta plus gamma y over P2. And Q3 star would be gamma over alpha plus beta plus gamma y over P3. So, in this problem, given this Cope-Douglas utility function, we will have same conclusions likewise. Something Q1, Q2, Q3 are all normal goods, right? Because the effect of y are all positive. And also, these three goods satisfy the law of demand. And all of them mutually are neither substitutes nor complements. They are independent. Okay? Any question here? Just remember this trick is a trick make us easy to find a solution. Okay? All right. So, hello. May I have your attention, please? Now we have a Cope-Douglas utility function, which is Q1 to the power of 2, Q2 to the power of 3, and the budget constraint is like this. So, just let me know quickly, how much would you spend on good 1? The total expenditure on good 1 would be, your income is $300,